At Hyundai Steel's bar mill in Pohang, modernization has transformed decades-old equipment into a system capable of producing premium bar stock for the automotive sector. The focus is now on special bar quality grades, where tight tolerances are the benchmark of performance. The process opens with billets heated to rolling temperature inside the furnace. These billets then pass through 14 stands, serving as roughing and intermediate mills. Cropping occurs several times along the way, ensuring quality from the leading to the trailing ends. It is striking how every stage connects seamlessly, like links in a strong chain. As the rounds progress, they enter the 3-roll precision sizing mill (PSM), installed as part of the modernization. 4 stands were repositioned to make space for the 5-stand PSM, designed to roll diameters ranging from 25 to 83 mm. Each stand surrounds the material completely, with individual drives guaranteeing uniformity. Hydraulic adjustment under load allows the roll gap to change in milliseconds, achieving tolerances far beyond DIN standards. The ability to adapt instantly under such stress leaves a lasting impression on any observer. Another feature is free-size rolling, allowing intermediate dimensions to be produced without additional passes. This flexibility reduces allowances for peeling and increases efficiency. The system is monitored by SMS's Technological Control System, TCS, which integrates seamlessly with Hyundai Steel's measuring equipment. Automation here feels both commanding and reliable, a rare combination in heavy industry. Roll changes also highlight the modernization. Prepared stands arrive from the roll workshop and are pushed in and out automatically. Not every change requires all stands, minimizing downtime and costs. The new stands couple with drives, media, and power supplies within minutes. The speed at which production resumes makes the entire setup feel almost unstoppable. Finally, finished SBQ bars are cut to customer lengths and transferred to the cooling bed. The rebar section remains in use for traditional output, but the PSM line now drives Hyundai Steel into higher value markets. Watching the red-hot bars settle into their final form brings a sense of power and achievement. It feels like industrial progress condensed into glowing steel.
In the world of oil exploration, the performance of a drill bit can determine success or failure. Design begins with digital simulation, balancing cutting forces and analyzing fluid flow. Engineers refine geometry to achieve stability in harsh downhole conditions. Casting follows, where steel or tungsten matrix is formed into solid bodies. Furnaces melt alloys, producing a base with both strength and toughness. Machining uses 5-axis centers from Germany and Japan. Threads, blades, and internal channels are shaped in one setup. For welding, patented carbide materials are applied to resist wear, impact, and corrosion. Layers fuse smoothly, creating a reinforced cutting structure. Final testing includes vibration, impact, and abrasion trials. Performance is measured against global petroleum standards. Polishing and inspection conclude the process, leaving each PDC or tricone bit shining, ready for the field. In this workshop, glowing steel is forged under hydraulic hammers, shaped with force and accuracy. Straightening ensures balance, then proof load tests confirm strength. Each elevator link emerges ready for heavy oilfield duty, unwavering in resilience. This video focuses on the production and capabilities of the Zani Servo Master 3200T, a high-capacity press built for large-scale industrial forming. The design phase was carried out by research and development engineers, working in collaboration with the Milan Polytechnic. Structural calculations were verified to ensure the press could endure the heavy forces it was designed for. It feels reassuring to see technical rigor applied from the very beginning. A key requirement from the customer was to consolidate several processes into one press. This shaped the evolution of the machine, creating a solution capable of handling multiple operations with efficiency. Such integration adds a sense of bold innovation. Production itself was divided between internal fabrication and specialized external suppliers. Heavy carpentry, boring, milling, and gear toothing were handled by trusted partners. Each stage reflects teamwork across different fields of expertise. The complexity of coordination underlines the importance of reliability in every component. Performance comes from combining servo technology with lever kinematics refined over years of development. This enables stable stroke control and flexible forming power. The balance of power and adaptability is striking. Finally, the press integrates an advanced mold-changing system. With its dimensions, strength, and optimized cycle, it stands among the most significant presses in Europe today. Its construction leaves a lasting impression of strength. The finished press embodies the drive to push boundaries further. Brass fittings play a vital role in fluid and gas systems, and their production demands a structured sequence of steps. At Cavaletto, the process begins with high-quality brass bars delivered to the facility, stored and selected according to dimension and grade. The first step involves cutting the bars into exact lengths for each component. Advanced saws ensure uniformity, preparing the raw stock for forging. The cut pieces are then transferred to heating furnaces, where controlled temperatures soften the brass for shaping. The glow of heated metal signals the energy of transformation. Forging follows, with powerful presses forming the blanks into their initial geometry. Each strike aligns material structure, adding durability to the fitting. Next, machining operations refine the surfaces and create threads, holes, or other required features. The machines hum steadily, a rhythm of accuracy and force. After machining, fittings undergo surface finishing, such as tumbling or polishing, to achieve smooth textures. Rigorous quality tests verify dimensional standards and leak resistance. Each finished piece embodies reliability that technicians can trust. Finally, fittings are packaged and prepared for distribution across markets. The craft of electrical pliers production opens with steel bars, each selected for strength and durability. These bars are heated until malleable, then cut into sections that will form the pliers core. It is fascinating how heat transforms rigid metal into a workable state. Forging marks the next stage, where powerful presses shape the red-hot metal into recognizable jaws and handles. Hammer strikes define the contours, giving the blank its first identity. Excess material is trimmed, leaving uniform shapes ready for refinement. Machining follows, opening with drilling and milling of critical holes for joints. Edges are refined, and the jaws are shaped to exact dimensions. Every cut and adjustment pushes the blank closer to its role in daily electrical work. Grinding smooths surfaces and ensures alignment. At this point, the pliers already resemble the final product. You can almost imagine how these pliers will feel in the hands of a worker. Heat treatment comes next, hardening the steel to withstand stress without losing toughness, quenching and tempering balance flexibility with resilience. The glowing metal plunging into coolant is a moment of raw intensity. Handles are then fitted, often with insulated grips to protect users from electrical currents. Finishing touches include surface polishing, tightening of rivets, and final alignment checks. Finally, each pair is packaged, ready for professional hands worldwide. Finally,
break all the way hard and aching, all the way hard and aching, all the way hard and aching.
The Seco 335.25 disc milling cutter handles complex slotting, face, and circular interpolation operations with remarkable efficiency. Its V-shaped insert design immediately catches the eye, promising enhanced performance and reduced cutting forces. A C45 steel workpiece is first secured in the milling machine, and the 125mm diameter cutter engages to create a precise slot, moving steadily along the designated path. Cutting parameters such as 165 meters per minute speed, 25mm depth, and 0.23mm per 2 feet guide each pass. Next, the cutter performs half-side and face milling, producing a smooth surface that highlights the tool's stability. Circular interpolation follows, expanding the machining scope to diameters between 200 and 220mm, demonstrating how the cutter can handle varying dimensions. It's impressive to see how the machine balances speed and control effortlessly. Watching the workpiece gradually acquire its shape is surprisingly satisfying, revealing the skill behind the machine's setup. Plunging along two axes completes the operation, ensuring consistent cuts and fine finishing. The V-shaped inserts maintain strong connection to the cutter body, allowing high-speed operations even under challenging conditions. Built-in wipers on the inserts leave surfaces free, reducing the need for secondary finishing. Adjustable pockets provide versatility for different materials, while four cutting edges lower cost per part. Every step showcases how modern disc milling achieves both precision and productivity. In aerospace manufacturing, the landing gear is among the most demanding components, requiring stability and strength under immense pressure. At the heart of this process, Tebis software integrates digital planning and CNC machining to transform a 2-ton forged steel block into the housing of a Boeing 777 landing gear. The sheer size of the raw piece already sets the tone for a remarkable production journey. The sequence starts with CAD preparation. Engineers refine the digital model to include all necessary details for machining. Tebis provides access to stored tool libraries and templates, automating the setup. It feels almost like a digital rehearsal before the real cutting begins. Next comes work planning. A virtual environment allows machines and tools to be selected with accuracy. Simulations detect collisions, confirm part geometry, and calculate optimal tool paths. The ability to foresee risks in advance makes the process more confident and precise. Roughing then removes excess steel using short and stable tools. Material tracking ensures no areas are overlooked during secondary roughing. Each pass across the steel block adds both force and control, an impressive sight to imagine. Finishing follows with 3+2 axis milling, refining the geometry to match aerospace standards. Here, smoother contours and tight tolerances define the component. The transformation from bulk steel to structured design feels powerful. Finally, all machining steps are logged into a digital work plan, documenting tools, operations, and sequences. This comprehensive record guarantees traceability and efficiency. Such documentation proves that modern aerospace is as much about data as it is about hardware. By the end, what remains is a landing gear housing that represents both strength and technological mastery. Among rows of heavy equipment, one machine stands out, the Okuma Multus B550, dedicated to the exacting process of spur gear skiving. This advanced equipment, part of Butech Bliss's investment, demonstrates how modern machining handles both strength and precision shaping. The process begins with digital programming that defines gear geometry. The machine's multi-axis design enables simultaneous turning and milling, reducing setups. Watching such integration feels both powerful and efficient. Cutting tools engage with controlled speed, removing material to form gear teeth. Continuous monitoring ensures stable operation. Each rotation adds a sense of progress unfolding step by step. The final product emerges with defined geometry, ready for demanding applications. The smooth coordination of tools and control systems is truly striking. It feels like raw steel transformed into ordered motion.
Shaping a cone from metal is both straightforward in its tools and intricate in its execution. In this production, the workshop demonstrates how a flat sheet transforms into a conical form through rolling and welding, a method that delivers structural stability as well as geometric precision. It is fascinating to think how such industrial work relies on principles of geometry learned in school. The sequence opens with flat sheet preparation. A measured piece of steel plate is laid out, cut to the required dimension, and edges are aligned. The plate surface glints under the shop light, waiting for its transformation. Even at this stage, the silent steel seems to hold potential energy, as if anticipating the forces about to shape it. The workers know that accuracy at this point will define the success of every following stage. Rolling marks the next stage. The sheet is passed through a set of rollers that gradually bend it along its length. Each pass tightens the curvature, turning a flat surface into a sweeping arc. The sound of steel shifting through rollers is deep and steady, echoing through the workshop like a mechanical heartbeat. Watching the curve form is like seeing rigidity melt into motion. The arc closes in upon itself until the edges nearly meet, defining the cone's outline. This transformation shows how even cold metal responds fluidly under persistent force. Joining follows immediately after. Welding binds the two edges, creating a seam that locks the shape permanently. Sparks burst across the seam, and molten metal pools momentarily before cooling into a solid line. Every flash of light feels like a reminder that heat can be just as much a tool as pressure. At the end, one cannot help but admire how basic steps yield such a commanding result. The making of an aircraft nose cone carries both heritage and technical depth, especially when it involves the legendary Spitfire. This restoration demands not only durable material, but also a method that respects traditional craftsmanship. In this case, XL metal spinning takes on the challenge with aluminum sheets, 3 mm thick, transforming raw material into a sleek cone for aviation history. The choice of material alone highlights the balance between strength and lightweight design. It feels remarkable that such a crucial aircraft element begins as nothing more than a flat disc of aluminum. Every stage reflects a dialogue between past and present, tying modern tools to wartime legacies. Production opens with the creation of a wooden former, selected because the project requires only a single bespoke unit. The aluminum disc is mounted onto the lathe against the wooden tool. As the lathe spins, the craftsman presses the metal with steady force, guiding it to take the shape of the former. The screech of contact between tool and disc cuts through the workshop, sharp yet rhythmic. The speed of the rotation creates a hypnotic rhythm, pulling the eye toward the forming cone. At times, the disc seems less like metal and more like fabric, folding and stretching under precise pressure. The gradual thinning and stretching allow the cone to emerge smoothly. Every push of the forming tool shows the direct dialogue between human skill and rotating metal. One can almost feel the vibration travel through the handle into the craftsman's arm, proof of the stubborn strength being tamed. Further shaping continues as the operator leans the tool into the disc, refining curves and adjusting angles. The cone's surface slowly gains elegance with each pass, as though guided by invisible lines. The spinning process inherently strengthens the aluminum by work hardening, which makes the cone resilient while remaining light. The strengthening effect is not only useful but critical for aircraft safety. It's a reminder that durability is born not from bulk, but from intelligent shaping. This balance of strength and lightness echoes the very philosophy of aviation engineering. Once the rough form is achieved, trimming removes excess edges, ensuring a clean rim for fitting. The lathe's sharp tool cuts away unwanted material with high accuracy. The cone now matches both size and geometry required for restoration. At this moment, the nose cone already carries the silhouette that once cut through wartime skies. That silhouette alone carries echoes of history, almost as if the plane's roar lingers within the metal.
A fully automated line prepares stainless steel sheets for the production of hot water tanks. The gleaming surfaces of the steel catch the eye, hinting at the care involved. Sheets are first shaped into cylindrical forms, aligning edges precisely for welding. Laser welding takes over, joining the seams with speed and accuracy that traditional methods struggle to match. Operators monitor parameters closely, ensuring each tank meets strict quality standards. Post-welding, tanks pass through inspection stations where any minor imperfections are identified and corrected. Additional processing, including surface finishing, prepares the tanks for final assembly. The synchronized movement of the system reflects the advanced engineering behind modern container manufacturing. Completed hot water tanks are then ready for shipment, exemplifying high-volume production combined with precise workmanship.
The forging of metal parts by hammer and die holds both raw strength and refined method. In this workshop, one can see how glowing steel bars are transformed into shaped components through repeated strikes and controlled handling. The sequence opens with heating, where steel billets are brought to a red-hot state in the furnace. The glow signals the right temperature, preparing the metal for shaping. Next comes placement on the lower die, where the billet rests in a cavity shaped for the part. With swift movement, the hammer descends, pressing the steel into form. Sparks leap at every blow, and the rhythm fills the air like an industrial drumbeat. The intensity of each impact reminds us how force and accuracy combine in every cycle. Final strokes refine the edges, bringing the forging to its intended outline. The rough part now carries strength, durability, and the promise of further machining. The assembly of the Master G8812 engine opens with rows of components laid out, each destined to play a role in generating power. Specialists align the engine block, inspecting surfaces before positioning crankshaft and pistons. Cylinder heads are secured, followed by valves and connecting rods, ensuring every channel and chamber fits its purpose. Watching the layers of parts merge into a single body carries a sense of inevitability. Final stages involve fastening covers, aligning systems, and preparing the engine for rigorous test runs.